Hello, my name is Garrison Graylick. This is video homework 2. The vector space R2 is not a subset of R3 because R2 is not even a subset of R3. The vectors in R3 all have 3 entries, whereas the vectors in R2 have only 2. So the set, as given, is a subset of R3 that looks and acts like R2, although it is logically distinct from R2. So you can see the figure there. The question is show that H is a subspace of R3. So to start, we're going to verify that H satisfies the 3 main conditions of the subspace. So first we want the 0 vector. I want to make sure that the 0 vector of R3 is in H. All right, so we got 0, 0, 0, and we can plug it in for S equals 0, T equals 0, and we can see that because of that 0 there, we do get the 0 vector. So that means that it is an element. Then we can move on to vector addition. We can have U equal S1 and T1 with our 0 as well, and then V equal S2 and T2. That'll also have the 0. So then what we can do is add them together, just like we normally do, and have S1 plus S2 and T1 plus T2. Now we can see that these are real numbers. So that means that this matrix right here is also an element of H. So that condition is also satisfied. And then finally we have scalar multiplication. So we chose our scalar, C, and then we're going to multiply that through. So C times S, C times T, CS and CT. Now we already know that S and T are real numbers. So if you multiply that by a scalar, it doesn't really change that. So CS and CT are still real numbers. And that shows that this right here, the scalar, is also an element of H. So that can show us that for this problem right here, H contains the 0 vector. It is closed under vector addition, and it is also closed under scalar multiplication. So this means that H is a subspace of R3. Next, we have problem 2. This asks us to show that the set H of all points in R2 of the form 3S and then 2 plus 5S is not a vector space by showing that it is not closed under scalar multiplication. Then find a specific vector, U, in H, and a scalar, C, such that Cu is not in H. So first, we're going to find our H vector. So I've got this here, and what we can do is we're going to set S equal to 1. So when we multiply that, 3 times 1, and then 2 plus 5 times 1, right? And that comes from this right here, right? That equation that was given. And we just get 3, 7. Now this is important because then we can use our scalar multiplication. We chose 2 as a scalar in this case, and multiply our scalar times our U vector. So that gives us an answer of 6, 14. Now, what we can do is check if this scalar is in H. So to be in H, it must be in this form right here. So 3S and 2 plus 5S. So that means what we can do, we see 3S equals 6. We can divide that 3, and we get S equals 2. Now, if we plug this in to this right here, right, this 3S, 2 plus 5S, we get 2 plus 5 times 2 equals 14. That's not right, right? 5 times 2 is 10 plus 2 is 12. 12 doesn't equal 14, right? So this condition is not satisfied. So then we can see that according to this problem right here, the set H is not closed under scalar multiplication. And since it's not closed under scalar multiplication, it is not a vector space. Our final question is number 3. Here we given the matrices shown, we got A, U, and V. Our first question is to determine if U is in null A, and could U be in column A? So first we're going to see if U is in the null space of A. We got this written down here. What we're going to do is do A times U. So there's our A matrice, and then there's U. And we got an answer of 0, -3, 3. Now this means that A is not in the null space, right? Because as we learned, if it was in the null space, we have 0, 0, 0. And since we don't have that, it is not in the null space. Next is the column space. Well, this one is easy because we can see that U has 4 entries, but A only has 3. Just from that right there, you can tell, because 4 and 3 are different, that no, U is not in the column space of A. So then we can move on to this next part right here. Determine if V is in the column space of A. And could V be in null A? So the way we're going to go about this is doing some row reduction. We're going to use AX equals B, just like we learned before. Here's our A matrix. Here's our X coefficients. And this is our B, which is in this case, our V vector right here, right? Since it asked for V. We're going to go ahead and set it up just like we learned how, right? And then solve it through. And I went ahead and did that on this page for anybody that wants to pause and study that. Now we can see that we have the echelon form of this matrix. So that means that V is in the column space of A because we will have an answer for this, right? We have the echelon form, so we know if we solve it out, we're going to get some answer. So V, yes, it is in the column space of A. Now the final part of this is V in null A? And again, we can look at this and see that V is not in null A because it wouldn't satisfy our equation, right? For the null space, we need this equation right here. A times V equals 0. Well, we can see this is a 3 by 1, right? And this is a 3 by 4 matrix right here, A is, right? And so we cannot multiply those together. So it's impossible for the product of those two to equal 0. So no, V is not in null A. Thank you very much.